Good afternoon, sir. I've made you co-host. Would you like to share your screen and check?
Just a minute.
Sir,
Yeah.
are you? I think you're muted. No. Can't hear you, sir.
Can you hear me? You can't hear me?
No, sir, you're not audible.
Hello. 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 Hello.
Hello. Yeah, good afternoon, sir.
Hello. Good afternoon. Good afternoon. Can you hear me?
Yeah, I can hear you, sir.
Okay. You can hear me.
Yeah.
Sir, I think you need to log out and log in again. Can't hear you. Am I audible to you?
No, but yeah, you are audible to me, but somebody else said she's
Can't hear you,
audible. She can hear me.
Yeah, it's me, Dr. Sonal. I can hear him.
Can anyone else hear it? Please put it in the chat box. Maybe something is wrong. Uh-oh. Am I audible to others?
Yes.
Now I can hear you. Something wrong with my AirPods.
Okay. Fine.
Keep them away, not get
Yeah.
Dr. Rajni, I've also made you co-host. If you can unmute and check for your screen share. Palagre sir, you also check for your screen share.
Yeah. I'll just check it.
Hello. Yeah, am I audible? Am I visible?
मैम आप ऑडिबल तो हो पर आपका वीडियो नहीं चल रहा.
Acha, can you see my screen?
Yes sir, I can see. Try
Is my
moving.
screen share okay? Okay, fine. Then
Visible, just try
sure.
to move your slides, sir.
Okay.
It's moving, sir.
Fine?
Yes, sir.
Okay, fine. So I will now stop sharing.
Yes, sir. Dr. Rajni, would you like to share your screen and check?
Dr. Sonal, I'm just doing it. Something is wrong with my camera, so I'm trying to open it on my laptop.
Okay.
Join within 2 minutes.
All right, ma'am. All right. Dr. Anuj will be joining. Dr. Aarti is traveling actually. So she won't be able to. Initially, her flight was at 5, but this thing has happened, so she's traveling now. So she won't join.
Okay.
Sir is joining. I just spoke to him.
Now you're visible.
Now you're
I'm
visible.
visible. And am I audible?
Yeah, you're audible and visible.
Try the screen share also, ma'am.
Yeah, that's I'm doing. She's made me the host. Make me the host again.
Okay.
Because I'm trying from separate system.
Okay, ma'am.
Oh. Yes. Slideshow.
Done.
Just try moving the slides, ma'am.
Yeah.
Yeah.
Great.
Yeah. Pictures.
ठीक है, ma'am. Dr. Anuj is joining in another 2 minutes and we'll start dot at 4.
Yeah.
Ma'am is traveling, so ma'am is not able to join. Good afternoon, Dr. Anuj. Happy to have you here.
Good afternoon. Good afternoon.
Very, very good afternoon.
Yeah, good afternoon, Dr. Anuj.
Good afternoon, Dr. Rajni and Dr. Pallav.
So we are all set to begin?
Yeah.
All right. So without much delay, I would now welcome Dr. Anuj Sharma and the two other speakers, Dr. Pallav Ray and Dr. Rajni Sharma, to this webinar at the start of the World Antibiotic Awareness Week. And I would request Dr. Anuj Sharma to set the ball rolling with a few words of introduction. Thank you, sir.
Thank you very much, Dr. Sonal. It's a pleasure to be part of this PG Masterclass and interact with the PG students of microbiology. All of you have a big role to play in antimicrobial resistance. And this is a very opportune time because today is the day before the World AMR Awareness Week starts. So 18th to 24th November is the World AMR Awareness Week. I'll come back to this in a bit, but I would also like you to understand AMR is a global priority. It's also a national priority. It is estimated that 10 million people will die every year by 2050 if we do not act now. And also the global burden of disease estimated that there were close to 5 million deaths in 1 year alone, 2019, out of which 1.27 million were directly attributable to antimicrobial resistance, more specifically, bacterial AMR. India has a national action plan. There's a global action plan in place. There's a national action plan in place. Second version, NAP AMR, the National Action Plan on AMR 2.0 is in the pipeline. And we expect to have that finalized and launched by the government probably by the end of this year or early next year. In addition, states are also working on their AMR action plans. 4 states already have their state action plans, and there are a number of other states which have either drafted their state action plans or they are working towards their state action plans. Rajasthan, Maharashtra, Sikkim, and a couple of other states have already drafted their state AMR action plans, and they are finalizing it, which will hopefully be launched soon. These are One Health AMR action plans involving other sectors as well. Now, a little bit about the World AMR Awareness Week. This is celebrated every year from 18th to 24th November. And this year, there's a slight change. Previously, this used to be called World Antimicrobial Awareness Week. From this year onwards, the name has been changed to World AMR Awareness Week. The acronym remains the same, WAAW. And the aim is to make AMR as popular as HIV, AIDS, etc., so that the common people understand what is AMR or what is antimicrobial resistance, what they have to do. And the aim of this, the World AMR Awareness Week, is to raise awareness about AMR. And as PG students, you can play a pivotal role because you understand AMR quite well, interact with other professionals to practice antimicrobial stewardship and diagnostic stewardship within your own institution and facilities, but also reach out to the patients and the community to raise public awareness, because the consumer behavior also contributes to AMR, where patients either take medicines on their own or they share their prescriptions, or they stop the treatment without against the doctor's advice once they start feeling better. So focus of the World AMR Awareness Week is primarily the patients and the public and the policymakers, but it's also a good time to reach out to technical stakeholders as well. as microbiology MD students, you can also contribute to AMR. Your primary role is primarily in ensuring that you are able to detect AMR in the laboratories, phenotypically as well as genotypically, and you have eminent teachers talking to you about this. Both Dr. Pallab Bray and Dr. Rajni Sharma have vast experience on AMR and a lot of other areas as well, in addition to AMR. Second is, after you manage to do the antimicrobial susceptibility testing, you need to generate antibiograms at the local level so that you are able to make sense of the data that you have in the form of antibiograms so that you can support your clinical colleagues in choosing the right antibiotic when they are treating infections. Also, practice diagnostic stewardship so that the clinicians use the microbiology laboratory optimally, partner with your clinical colleagues, especially ID physicians, critical care doctors, as well as nurses to practice antimicrobial stewardship, diagnostic stewardship, and infection prevention and control. Infection prevention and control, or IPC, is another area where you can play a big role, as well as antimicrobial stewardship. These are the three main strategic priorities of India's National Action Plan. Priority 2, 3, and 4. You can also play a role in research through your thesis topics if you are working on AMR, as well as raising awareness and trainings, which is priority 1. And also be part of collaborative efforts to tackle AMR, not just in human health, but across other sectors with a One Health approach. So I would like to stop here now, and I would like to thank Dr. Sonal Saxena, Secretary IAMM, who's also the coordinator for DENSAR, the Delhi Network for Surveillance of AMR. This was actually founded as WINSAR-D, WHO IAMM, a network for surveillance of AMR. And their data has already been published and is also being submitted to NCDC, which is the National Coordinating Center for AMR Surveillance, and also shared at the global level in the global AMR surveillance system. So thank you very much for inviting me, Dr. Sonal, and all the best to this PG Masterclass. I'll switch off my camera, but keep listening in.
Thank you, sir. Thank you for these kind words of introduction. The first speaker today is Dr. Rajni Sharma, Senior Professor at the Department of Microbiology, SMS Medical College, Jaipur. And she will be talking to you on molecular mechanisms of antimicrobial resistance in GPC and GNR. As you all know, we try to include the topics which are of your, not only your day-to-day practice importance, but also from your exam point of view. And this is, I think ma'am and Dr. Pallab would agree with me, this is a topic which is covered multiple times in the paper, not only in one paper, but it is also covered in paper 4 in recent advances. So over to you, Rajni ma'am, for continuation of the show.
Yeah, thank you, Dr. Sonal. Thank you for giving me this opportunity. And as rightly said by Dr. Sonal, this is a very important topic and grossly covered, and is very important for theoretical point of view as well as for your practical point of view, because as just described by Dr. Anuj, the intensity of the problem of AMR, we all know that we are at the dead end, and the pipeline for new antibiotics has already been dried up. So for judicial use of antibiotics, we should know the mechanism of resistance, how these bacteria, they are attaining resistance to most of the antibiotics which are available for us today. So the intensity of the problem, where we are heading, we all have just heard from Dr. Anuj. And it is prudent to acknowledge that over 3 million deaths in India are from preventable infections. So this is a very scary picture. So we should understand what this problem is. As just told, this has been declared as global crisis and has been put in top 10 global public health threats facing humanity by WHO. And due media coverage is also given to this problem, because as we know, this is an invisible problem. This is an invisible pandemic. And but recently, even media has started acknowledging the intensity of this problem. ICMR says that resistance to last resort antibiotic is growing in India. So all these figures are really scary. So to understand what is antibiotic resistance, or how different bacteria, different classes of bacteria develop resistance to different classes of antibiotics. So this is my first slide, that antibiotic resistance, we can say this could be intrinsic resistance, that is innately bacteria are resistant to certain antibiotics due to lack of metabolic process, target site, or innate efflux mechanism. Then the other mechanism which we divide is second category is acquired resistance. This could be genetic, by genetic methods, which could be chromosomal mutation, which can bring change in efflux pump, permeability, or target mutation, a modification. Or this could be even extra chromosomal methods in the form of horizontal gene transfer. That certain biochemical methods are also responsible for acquired resistance by producing various enzymes or preventing drug accumulation or modifying target sites. So we will go into depth of all these methods. They are very important for different classes of antibiotics. Now, when we say intrinsic resistance, certain organisms, they have intrinsic resistance to certain classes of antibiotics. Suppose you are dealing with colistin resistance in your laboratory. First thing which should come in your mind, that whether you are dealing with the organism is the type of organism which has intrinsic resistance to colistin, and the most important is Proteus vulgaris or Burkholderia cepacia. Similarly, as shown in this table, different organisms, they have resistance, intrinsic resistance to these groups of drugs. Suppose if you are dealing with methicillin resistant Staph aureus, then it is resistant to all beta lactams. Then this is just the pictorial depiction of intrinsic mechanism of resistance. As you can see, antibiotic A, it can enter the bacterial cell, but it cannot combine with penicillin binding protein, so cannot execute its effect. Second, antibiotic B can enter the bacterial cell, but at the same time, it is thrown out of the cell by efflux mechanism. And the third, antibiotic C, it cannot even enter the bacterial cell. So these three are the basic mechanisms which represents the intrinsic resistance by the bacteria. So bacteria acquire resistance either by environmental exposure or due to selective antibiotic pressure. We all know whenever antibiotics are given, the sensitive population is killed. But if any resistant population is there, they will multiply and they will constitute the majority population. Now, this is a beautiful diagram which represents the cell wall. Basically, this is cell wall of gram-negative bacteria. And bacteria can express more than one mechanism of resistance, leading to either multi-drug resistant organism or even pan-drug resistant organism. Pan-drug means resistant to all the available classes of antibiotics. Now, here you can see, number one, that reduced number or differential expression of porins or decrease influx. In order to act against bacteria, first antibiotic needs to enter the bacterial cell. So if the entry of antibiotic is stopped at the end, antibiotic entrance is stopped, and this is especially seen with beta lactams, then antibiotic resistance is produced. Once antibiotics enter the bacterial cell via outer membrane, then there are certain mechanisms which are called efflux pumps. If there is increase in number of efflux pumps, then before acting, these antibiotics are thrown out of the cell. And the third important mechanism is altered target binding site. So each antibiotic has a specific target over which that antibiotic combine and kill the bacteria. So alteration of this target binding site result in antibiotic failure. And we all know, you must have heard that various enzymes are there. Various beta-lactamases, ESBL, carbapinamases, NDM, MCs, various enzymes are there. These enzymes, they kill the antibiotics or they deactivate the antibiotics. So this is just a summary of different mechanism of resistance. So there are basically two major genetic strategies which bacteria apply. One is the mutation in gene, and second is acquisition of foreign DNA. Mutation of gene can result in modification of antibody molecule, decrease in drug uptake or influx, activation of efflux mechanism, and modification of antimicrobial targets. This is decreasing affinity of the target. And the second, that is the acquisition of foreign DNA. This is mainly done by transformation, transduction, or conjugation. And the conjugation is the most important method, which is usually seen in hospital environment, in which where by cell-to-cell contact, genes are transferred from one bacterium to another. And this uses mobile genetic elements, which we call MGEs, as vehicle. And the most common are plasmids and transposons. When we come to mutation as a mechanism of antimicrobial resistance, as I just briefed you, that first is the modification of antibiotic molecule. This can occur in the form of chemical alteration of antibiotic or destruction of antibiotic molecule. So this diagram shows the first picture is the antibiotic molecule can bind to its target and execute its action. The second picture shows that due to either degradation by enzymes or by modification of antibiotic molecule by addition of some chemical group, antibiotic molecule cannot combine with its target. So modification in antibiotic molecule can result in resistance. So this chemical alteration of antibiotic is done as bacteria produce certain enzymes which induce chemical changes to the antimicrobial molecule. This type of mechanism is seen in gram-negative as well as gram-positive cocci, mostly against antibiotics that exert their effect by inhibiting protein synthesis at ribosome level. And usual chemical changes are in the form of acetylation, phosphorylation, or adenylation, which result in steric hindrance that decrease the avidity of the drug for its target. And most important are aminoglycoside modifying enzymes. These enzymes are harbored on mobile genetic elements, and they are associated with resistance to aminoglycosides or even to all the aminoglycosides together, and are found in enterococci and staphylococci, and accounts for the high level gentamicin resistance in enterococci, that is in VRE strains and MRSA. So again, this is the pictorial representation. On the left-hand side, you can see the red antibiotic. It combines with the target protein and execute the action. On the right-hand side, you can see the modification of antibiotic molecule, either by degradation or by addition or modification of the structure of antibiotic, prevents it from binding to its target and results in resistance. Then the second method is the destruction of antibiotic molecule by production of certain enzymes. This is the main mechanism of resistance for beta-lactam antibiotics. Beta-lactamases are the enzymes which are produced by commonly produced by Enterobacteriaceae, and they were first described in 1940s, just before the penicillin was introduced. These enzymes, they hydrolyze beta-lactam in periplasmic space, thus prevent penicillin binding protein inhibition. No, we all know wide spectrum of beta-lactam compounds. They were discovered since the discovery of penicillin in 1928. Large number of beta-lactam compounds were discovered, and at the same time, beta-lactamases also came into action. So certain compounds which were less susceptible to beta-lactam, such as ampicillin, was discovered, but again, during 1960s, new plasmid-coded beta-lactamases capable of hydrolyzing ampicillin was found, and this was termed TEM1. Then again, various with further discoveries, various new generation beta-lactamases were discovered, but soon they were followed by rapid appearance of enzymes which were capable of destroying them. And this is the classical example of antibiotic-driven adaptive bacterial evolution. Now, this is a very beautiful diagram. On the left-hand side, you can see the antibiotic discovery. So after 1928, large number of antibiotics were discovered till 1990. After that, you can see very few antibiotics were discovered, and there is a big discovery void now. Whereas on the right-hand side, you can see antibiotic resistance. So you can see simultaneously, within few years after discovery of antibiotic, the resistance mechanism, bacteria develop resistance mechanism, and they become resistant to these antibiotics. So this is how, or what we call the antibiotic-driven adaptive bacterial evolution. Now, this beta-lactamases, the gene which code for beta-lactamases are termed BLA, and they are followed by the name of specific enzymes such as BLA KPC. KPC is the enzyme and BLA is the gene. They were found both on chromosomes as well as mobile genetic elements, or they may be as a part of integrons. We classify beta-lactamases as per Ambler classification, which is a widely used classification and most practical one, into 4 classes, A, B, C, and D. When we talk about class A beta-lactamases, this includes enzymes from narrow spectrum beta-lactamases to enzymes capable of destroying almost all beta-lactams, including carbapenems. And it includes penicillinases, ESBL, CTXM, or carbapenemase KPC. What happens here, that original enzyme, it evolves into a novel enzyme. Now, just as we talked about TEM1 penicillinase, which was discovered in 1960 against ampicillin, this enzyme, it evolved due to mutation, and it transformed into TEM3. And this after acquiring the ability to hydrolyze 3rd generation cephalosporin and estrionam. And such enzymes are put into class which are known as extended spectrum beta-lactamases, or ESBLs. ESBLs are resistant to penicillins, 3rd generation cephalosporins, and monobactams, but no activity against cefamycin and carbapenems. They are generally inhibited by clavulanic acid and tazobactam. The CTXM is plasmid-coded, most prevalent ESBL worldwide, and are majorly responsible for cephalosporin resistance in E. coli and Klebsiella pneumoniae. Then another important enzyme in this group is carbapenemase. Unfortunately, now we are even getting carbapenemase resistance. These carbapenemase, they hydrolyze carbapenems, which are the most potent beta-lactamase. We can divide them as serine carbapenemase, which include Ambler class A, C, and D, and metallocarbapenemases, which include class B. The KPC of this class was first reported in 1996 in Klebsiella pneumoniae, but now reported in other GNB as Enterobacter species, E. coli, Proteus mirabilis, Salmonella species, and also found in Pseudomonas aeruginosa. So here you can see, along with the development or discovery of new antibiotic, the resistance mechanism or resistance enzymes are already there. And this resistance mechanism is not only limited to that particular organism, initially found in one organism, and it rapidly spread to other organisms also. Then class B, these are metallo-beta-lactamases, because they utilize a metal ion, usually zinc, as cofactor to attack beta-lactam ring. They are active against carbapenem, and they are inhibited by EDTA. Now, important metallo-beta-lactamases are IMP, VIM, and NDM. During 1990s, these enzymes, IMP and VIM, were reported in Enterobacteriaceae, Pseudomonas, and Acinetobacter. And genes encoding for these enzymes have been found as a part of accessory genome of pathogenic bacteria, which suggest horizontal gene transfer. VIM, then NDM, we are very familiar with the term NDM, or New Delhi metallo-beta-lactamase, first identified in 2018 in Klebsiella pneumoniae from a Swedish patient who had been previously admitted to hospital in New Delhi. That's why it's given the name NDM, or New Delhi metallo-beta-lactamase. The very characteristic feature of this type of resistance, or this gene, is that BLA-NDM genes are found in several plasmids and are readily transferred among gram-negative bacteria, which is of major concern. Although after the discovery of NDM, measures were taken all over the world to stop the spread of this resistance mechanism, but everything was failed, and this has spread rapidly globally. And MGE carrying gene for NDM carry multiple other resistant determinants as gene for carbapenemases, VIM, OXA, ESBL, and AMEs. So presence of NDM1 is frequently accompanied by an MDR phenotype. Then class C are MCs, found mainly in Enterobacter cloacae, Klebsiella aeruginase, Citrobacter, Serratia, Providentia, Morganella morgani, and Pseudomonas aeruginosa. Class D beta-lactamases, they are again gaining importance. They hydrolyze oxacillin. They are poorly inhibited by clavulanic acid. 3 important variants are there. clinically important variants are there, which are found in Pseudomonas aeruginosa, OXA23 in Acinetobacter baumannii, and OXA48, initially found in Klebsiella pneumoniae, but now found in Enterobacteriacea and Acinetobacter baumannii also. They are coded by genes found on MGs. They're particularly prevalent in Acinetobacter baumannii, but now they have been reported in other clinically relevant organisms, such as E. coli, Enterobacter species, Klebsiella pneumoniae, or Pseudomonas aeruginosa. So this is the pictorial representation of Ambler classification, how they are divided into 4 classes and which examples are there for each class. Then the second method is decreased antibiotic penetration or decreased influx. Bacteria have various mechanisms to prevent antibiotic from entering the cell by decreasing the uptake of antibiotic molecule. And this is very common or important for gram-negative rods because they have very thick cell wall, which limits the influx of the drug. Now, outer membrane acts as the first line defense. GN are intrinsically less permeable to various antibiotics, and they use water-filled channels, which we call porins, to enter the cell. By reducing the permeability of the outer membrane and limiting the antibiotic entry into bacterial cell by down-regulation of porins or replacement of porin by more selective channel is established method of resistance in gram-negative bacteria. In Enterobacteriaceae, Pseudomonas, Acinetobacter, this reduction in porin expression contributes majorly to resistance to carbapenems and cephalosporins. This is besides enzymatic degradation. And this mechanism, that is decreased antibiotic penetration or influx, is a very important resistance mechanism which is seen during treatment. Now, one day you have reported an organism as sensitive. Within 24 to 48 hours, if you again repeat the sensitivity, sometimes you get resistance. So during the course of therapy, even bacteria, they mutate and they develop certain changes such as porin loss or downregulation of porins, due to which the previously sensitive strain become resistant. So decreased antibiotic penetration or suppression of efflux is very important. And basically this is seen, that is during therapy, shift of porin expression is seen from OMPK 35 to 36, and 36 are smaller size channel. So influx of bacteria is inhibited. Again, the vancomycin, which is not active against gram-negative, is due to lack of penetration through outer membrane. Again, this diagram shows in resistance bacteria, influx influx is decreased due to mutation or decreased expression. And efflux is again, which I'm going to talk next, that efflux is again important mechanism of that is drugs are thrown out of the bacterial cell immediately. So efflux pumps are activated and they are major contributor to antibiotic resistance. So activation of efflux pump, bacteria extrude toxic compounds in drugs. Example, efflux of tetracycline out of cytoplasm of E. coli, which was first described in 1980. This mechanism is found common for both gram-positive and gram-negative pathogens. Again, this mechanism of resistance is applicable for many classes of antibiotics, those which are protein synthesis inhibitors, fluoroquinolones, beta-lactams, carbapenems, and even polymyxin. Gene coding for efflux pumps are located on both MGs and on chromosome. Chromosome encoded pumps are responsible for inherent resistance to particular antibiotics. A classical example of this is E. faecalis to streptogramin A. Then multi-drug efflux pumps are also there, especially found in Enterobacteriaceae and Pseudomonas aeruginosa. And the genes coding for multi-drug efflux are usually carried on plasmids. Then again, tetracycline resistance is due because of this activation of efflux pump due to TET efflux pumps. Then due to MEF gene, which is found in strep pyogenes and streptopneumoniae, S. pneumoniae, resistance to macrolide is seen. Again, this, as I told earlier, that this efflux mechanism of resistance is also very important during the course of antibiotic therapy. So at the beginning of the therapy or during therapy, these organisms, they develop resistance. Another important aspect of this increased efflux is this same efflux pumps transport a wide range of structurally similar substrates and are known as multi-drug resistant efflux pumps. So such pumps are associated with multi-drug resistance. An example is seen as Stenotrophomonas maltophilia, Klebsiella pneumoniae, and Staph aureus. Then the last method of resistance is change in the target site. As we all know that antibiotics need to combine with their target site before initiating the action. And this is a common strategy for bacteria to develop AMR is to avoid the action of antibiotic by interfering with their target site. This can be done by protection of the target, that is preventing antibiotic to reach its binding site, or by modification of the target site that result in decreased affinity for the antibiotic molecule. Now here in this diagram, you can see the antibiotic is combining with its target site, but on the right hand side, you can see due to modification of the target, target is protected, so antibiotic cannot combine, or another protein which can perform same function is synthesized. So antibiotic molecule, even if it has combined with the target, there is no inhibition of cell wall synthesis because the other protein is carrying out the function. Again, this diagram shows the target site change, how it affects. On left-hand side, you can see the mutation in target site result in failure of binding of antibiotic molecule to its target site, or any chemical changes in the target site can result in failure of binding of antibiotic to its target site. Now, this target protection is usually seen with tetracycline resistance and quinolone resistance. Tetracycline resistant determinants, such as TET-M or TET-O protein, they interact with the ribosome and dislodge the tetracycline from its binding site. Then quinolone resistance protein, QNRs, they were first described in Klebsiella pneumoniae. They act as DNA homology that competes for the DNA binding site of the DNA gyrase and topoisomerase 4. This reduction in the DNA gyrase and DNA interaction decreases the opportunity of the quinolone molecule to form and stabilize the gyrase cleaved DNA quinolone complex, which is lethal for the cell. So this is how the targets are protected by these proteins and antibiotics are displaced. Then modification of target. This is again one of the common mechanisms for AMR in bacterial pathogen, and it affects all the families of antimicrobial. And major changes are in the form of point mutation in the gene encoding the target site, as seen with fluoroquinolones and linezolid resistance, or enzymatic alteration in binding site, such as addition of methyl group, as shown in this diagram below. That is at antibiotic combining site, if there is methylation of the target, then antibiotic cannot combine. Then replacement or bypass of the original target. Bacteria are capable of evolving new targets that accomplish similar biochemical functions of the original target, but are not inhibited by the antimicrobial molecule. The classical example is vancomycin-resistant Staph aureus. Then changes in antibiotic target by mutation is usually seen with linezolid resistance. Linezolid normally targets 23S ribosomal RNA subunit of gram-positive bacteria. Mutation in gene coding for 23S RNA results in resistance, and this type of resistance to linezolid is seen usually in Strep pneumoniae and Staph aureus. Again, linezolid resistance in MRSA, rifampicin resistance or penicillin resistance in S. pneumoniae, and gonorrhea is mediated through mutation of target. This is very important mechanism of resistance, especially when we are talking about gram-positive organisms, that is complete replacement or bypass of the target site. Bacteria evolve new targets that perform same biochemical function of the original target, but are not inhibited by the antimicrobials. And the best example is methicillin resistance in Staph aureus, which is due to acquisition of a gene, that is MEC-A gene, which encodes the beta-lactam insensitive protein PBP2A. This protein enables cell wall biosynthesis despite PBB being inhibited by the presence of antibiotic. So whenever Staph aureus acquire a gene, MEC-A gene, it directs to the formation of different target proteins. Instead of PBB, PBB2A are produced, and these PBB2A are insensitive, beta-lactam insensitive. So even if drug is given, bacteria continue to synthesize cell wall as they have produced separate targets which perform the original function. Similar, the second example, very important example in this category of mechanism of resistance is vancomycin resistance in enterococci. VRE is due to Ven A gene cluster, which contain many genes, Ven A, B, D, E. And these, the basic mechanism is little different here. Instead of combining these glycopeptides such as vancomycin or teicoplanin, instead of combining with the PBBs, they have different target. They bind to D-alanine endings, and they inhibit cell wall synthesis and cell death. Then remodeling of this site prevents vancomycin from binding to target. And this type of resistance is typically seen with E. faecium. So instead of combining with PBBs, these glycopeptides, they combine with DLA endings. And if there is, because of change in the target site, the bacteria, they produce D-lactate. So these endings are changed. So these drugs cannot combine to the changed target sites. Then one more important mechanism to bypass the target site is the bypass the metabolic pathway that antibiotic inhibits by overproducing the antibiotic target. We all know that trimethoprim sulfonamide typically act through metabolic pathway. So they produce different metabolic pathway, and so drug cannot act against them. Now we all know the polymyxin B or polymyxin E, which is colistin. These are available as the last resort drugs. They are active against gram-negative bacteria, but they have been used widely nowadays because we are encountering multi-drug resistance or even pan-drug resistant organisms. So these drugs are widely used. So resistance is emerging to these drugs also. They specifically bind to lipopolysaccharide. So antibacterial activity is due to hydrophobic chain, which disrupts the cell membrane. And resistance is associated with the changes in the expression of regulators affecting lipoprotein saccharide protection, which result in alteration in the target and reduce binding of the drug. So the mechanism of resistance to this drug is totally different. It acts through lipopolysaccharide, and alteration in these expression of these lipopolysaccharide result in failure or target failure. So this is just to conclude the different antibiotic resistance mechanism. This is a very beautiful diagram. Now, right from at the entry, if we can see if there is loss of porin, this type of resistance is typically, this mechanism of resistance is typically seen with carbapenems, imipenem. Then there are certain beta-lactamases. Once the drug enters the periplasmic spaces, then there are certain beta-lactamases in periplasmic spaces, which include carbapenemase or some other beta-lactamases, which again degrade the drug. Then overexpression of transmembrane efflux pump, which throws out the drug. And this is usually seen with beta-lactams, meropenem, quinolone, aminoglycoside, tetracycline, and chloramphenicol. And of course, we have antibiotic modifying enzyme. As we just talked about, this is good for aminoglycosides and ciprofloxacin. Aminoglycoside modifying enzymes are there. Then target mutation, we just talked about target mutation. This is seen with quinolones. Because of DNA gyrase or topoisomerase 4 modification. Then we have bypass targets, as this is seen with trimethoprim sulfamethoxazole. And lastly, mutation in lipopolysaccharide structure, which is responsible for resistance to polymyxin class of antibiotics. Again, this is a very comprehensive diagram of which covers the mechanism of resistance, both intrinsic as well as acquired at different levels. No, this table just summarizes, as I told in the beginning, only single mechanism of resistance is not there. Multiple mechanisms act whenever an organism becomes resistant to a particular antibiotic. So in staphylococci, different mechanisms are there, such as drug inactivation, target replacement, especially when we are talking about vancomycin, or target modification for linezolid, or changes in cell surface adaptation for visa or daptomycin. In enterococci, for enterococci also, for beta-lactam, drug inactivation with the help of various enzymes, or for vancomycin, target replacement is important. and even for beta-lactams and linezolid target modification. Streptococci target modification is very important for beta-lactams and linezolid. Now, I'll just talk about two important organisms, like this one is for Pseudomonas and Acinetobacter. For Pseudomonas, again, different mechanisms are there. Both chromosomal mutation and MGE acquisitions are responsible for resistance to various drugs. So either the MC-mediated resistance or by other beta-lactamases in the form of penicillinases, ESBLs, or production of metallo-beta-lactamases. Again, loss of porin is responsible for, especially for imipenems, increase efflux pump for various drugs, and lastly, the important for polymyxin, that is lipopolysaccharide modification. So different mechanisms are working for different group of drugs. Then this is for Acinetobacter, again, high level expression of MC, high level expression of OXA51 beta-lactamase, and other beta-lactamases as extended spectrum beta-lactamase, metallo-beta-lactamases, and as I just talked, oxacinylase type carbapanases are also very important. Then functional loss of porins, increase efflux, again for different drugs, and again for polymyxins, lipid or lipopolysaccharide modification is important. So just a few lines about visa and versa. We know that nowadays we are encountering Vanco intermediate resistant Staph aureus. So when Vanco concentration, when it is not inhibited by Vanco concentration below 4 to 8 microgram per ml, sorry for the mistake, and we call them visa. They were first identified in 1996 in Japan, and they are associated with the presence of thickened cell wall rich in peptidoglycan chain. And this DLR residue in thickened cell wall act as a decoy target that block vancomycin in external layer and divert it from reaching to its true target. Similarly, now we are encountering vancomycin resistance Staph aureus also. These versa they have acquired when A gene from VRE, which codes for the terminal DLR-DLECT. I just told you before that instead of DLR-DLR, the target is changed. So DLR-DLECT is there. So they cannot bind with this target, and which results in vancomycin resistance. So that's all from my side. Different mechanisms of antibiotic resistance.
Thank you so much, ma'am. It was very, very interesting and made very, very simple. I'm sure the students must have benefited it a lot. There's just one question for you. Somebody wants to know, do we have carbapenemases in class C?
Let me just show you. This diagram is very self-explanatory. Yeah. So this is class C. Class C has only MC. Carbapenemases are there in class A, D, and B in serine, this thing. But in class C, only MC is there.
Thank you, Dr. Rajni. Could you just stop sharing?
Yeah.
So with that, I think you are quite clear with the terminologies that are there
Stop kar.
and with the various mechanisms that we have.
Share kar diya. Pause share kar diya.
So I think now I will start with the basics of AST. I know it's going to be a little exhaustive for you all today, but we thought that we'll cover all the So I'm going to take some time and talk to you about the basics of antibiotic sensitivity testing. And if time permits, then I will touch upon CLSI. Otherwise, I will schedule another session maybe next month for the purpose of covering the CLSI basics. So hope I'm audible to you all. So when we think of AST, why do we do AST? Our primary goal is to offer a guidance to the physician who's seeking an effective antimicrobial therapy. I always tell my students, AST is your bread and butter. This is what is going to pay you for life, because the physician is not interested in what you're doing in the lab. He's more interested in finding out what I can offer to my patient. And on one hand, he wants to know what he offers. On the other hand, he has to be competent enough to read what you're writing. Sometimes what a microbiology write may not be interpreted in a right manner by the clinician and may lead to an ineffective or an irrational therapy. So any bacteria which has been isolated from clinical specimen and the susceptibility to it, if you are able to provide, but the organisms which are colonizers and which do not have, which probably have a predictable susceptibility to antimicrobials. For example, Streptococcus group A or Corynebacterium diphtheriae. In that case, you don't do ASTs and don't report, and you have to make a physician understand that too. And we all know that there can be a difference in vivo and in vitro. The drug concentrations are different in the body. There is a protein binding, the duration of the drug exposure. In the laboratory, there is a 18-hour exposure, but in the body, the exposure may last for about 6 hours or 18 hours, depends on the post-antibiotic effect, depends on the PKPD in that particular patient, the renal status, the liposomal enzyme in the liver status. So various physiological conditions, and then how the host responds to that infection by itself is also a factor which is going to determine your in vivo. And very often you will hear from the clinician saying that you gave this particular sensitive drug, but my patient is not responding, or the vice versa, that although you said it is resistant to this drug, but I continued him on and he recovered. So you have to understand that there is no EGO here. There is a simple method that the body cannot be replicated in our laboratory of 18 hours, but we try and simulate as much as possible. The growth conditions and the inocula will determine as to what is there at the exposure. But before starting the AST, think about a few issues. Think about what is the organism, what is the site of infection, which antimicrobials are you going to use against that drug-bug combination, and what is the method that you're following, and how do I report the quality assured results. Because unless and until you report a quality assured results, you will not be able to, your physician will not trust you. And that trust is very, very important when you're dealing with a patient. So when we select an AST methodology as a microbiologist, what should be in our mind? It should be easy to perform. It should not be complicated technology or a complicated methodology that our technical staff is not able to do or requires sophisticated training. It should be flexible enough that you can do it maybe in a lab which has very little load or has very little equipment, and to a tertiary care system. The cost should be bearable, especially for a developing country or LMIC like ours. It should be reproducible. Today, if I do a particular sensitivity using the same combination of drugs and drug-bug combinations and media, the similar results should be obtained by another laboratory as well. And so they should be accurate and reliable, because after all, you are playing with lives here. They should be adaptable to automated and semi-automated, and Dr. Pallabray is going to cover this portion, how the AST is adapted to automated or semi-automated systems. And there should be a validation data for the range of organisms to be tested. Very often you think about this condition, and PGs have asked me also why we don't have Indian guidelines. Now that is going to take a lot of data for you to validate before you produce your own Indian or LMIC guidelines. And we are all familiar with these technologies. We are familiar with diffusion methods, dilution methods, molecular methods, and automated methods. So I'm going to cover basically diffusion method. Dilution methods I'm not covering because they are a talk by itself. The advantages are that they are low in cost. It's very easy to modify these. Suppose today I want to do minocycline instead of tetracycline, I just have to change a disc. It's not going to work much high. It works very, very well with a very limited technical support in a very high load laboratories, and allows you to add or delete antibiotics. If the clinician wants a particular antibiotic, for example, they want meropenem instead of imipenem, you can do that. It's not that you have to change something in the system or anything. And it can screen for a subset of isolates. For example, suppose you want to give MICs only for ICU patients. You put up an automated system, or you want to run the MICs, you screen them. Suppose you have a resource constraint and you want to do then MICs for a particular set, for example, vancomycin resistance or colistin resistance, which have to be done by MIC. Other than that, you can isolate make a subset and then do it. So we all know this, that the rate of diffusion will depend on the drug, whether it is a heavy drug like ticoplanin and vancomycin, on the soluble properties as to what they are how much is their solubility in the water or in the media that is there, and also on the molecular weight of the drug. What is the molecular weight? Is it a heavy drug or a slow drug? What is the inhibition zone? Inhibition zone is directly proportional to the bacterial susceptibility of the drug in the disc and will depend on this diffusion and solubility. Very often, students have a very basic query as to how the MIC and the disc diffusion have been aligned. So if you look at this table, it's quite clear that you have a sensitive MIC, which you can see here as 4, and you have a resistant MIC, which is maybe say 12 or 8, which is seen by the second horizontal line. Now, if you see here, when these validation data points were developed, they kept doing the susceptibility by the disc diffusion, taking out various strengths of these discs, and they found that at a particular disc, all those which were sensitive, that means below 4, were showing a zone size which was say above 22. So this is how it was taken as a sensitive zone, and they were given as a sensitive zone. Now, when the similar point, if you look at the resistant part, you will find that these became resistant because all these which were above the MIC were showing you a zone size which was less than 20. And in between, you got your intermediate zone. So this became your resistant. So that is how the Stokes or Kirby-Boyer has been aligned to your MIC, and it actually reflects your MIC to a large extent. But then what is the difference between the two? Again, for historical purposes, now we don't do Stokes anywhere. So the control is on the same plate, so you can make out whether your disk is working or not. It is easy and cheap because you don't require MHA. You can also use neutron agar for this. You can use in-house disks for use because you're using the same working control. Kirby-Boyer, on the other hand, you put your control separately, and I'm not going to talk about QC. That's a next month's topic, and we will have another speaker to talk about QC for this part. So what are our requirements? And all our requirements are going to determine what exactly we make. My guide used to say, microbiology is all about kitchen, Sonal. If you have good ingredients, you make good food. And you have good technology, that means if you have good equipment or if you have good training, then the chef training, it equals equivalent to chef training, and you get a good food. So all the material that you require is here. You need McFarlane standard, you need Vikram cards, you need Muller-Hinton agar plates, and so on and so forth. What does CLSI recommend for media? It recommends these different media. For Gono, it recommends GC agar base with growth supplement. For pneumo, it recommends MHA with 5% or defibrinated horse blood. Very often I've asked my students, what is a defibrinated horse blood? And so you must know these terminologies when you're using this to the examiner. But majority of the time we use this for all non-fastidious organisms. We use Muller-Hinton agar. Now, why do we use Muller-Hinton agar is that the beef extract and the casein make it a very nutritively good medium. The starch which is there absorbs any toxic metabolites which are there, and hydrolysis of this starch, it results in dextrose, which serves as a source of energy for the organism. So it grows very well, and it grows uniformly well. Agar, of course, is the solidifying agent. And you also have a fastidious Muller-Hinton agar, which which contains 5% mechanically defibrinated horse blood with beta NAD, for which you may need it for Streptococcus pneumoniae or viridans or Haemophilus influenza, Campylobacter, Aerococcus, and Kingella. Now, so it is a non-selective, non-differential medium. A starch also affects the rate of diffusion, gives it a uniform diffusion, provides better nutrition. It has slightly loose agar as compared to Columbia agar base or Newton agar base, so there is a better diffusion of the antibiotics, and there is an acceptable batch-to-batch reproducibility. Not very much it is, and it is cation adjusted. It has to be low in PABA and thymine and thymidine contents. Why this happens is we'll talk about later. Now, always remember that the media should be poured to a uniform depth of 4 plus minus 0.5 millimeter. Now, why this is there is because you need a standardized system. You need a system where everything has been standardized. So your zone sizes are standardized on a media which is this thick. Not on a, and for this, for a 90 mm circular plate, you will require approximately 25 mm. So you have to remember this. Otherwise, what happens is your zones will be larger or thinner. And so what does PABA does? PABA can antagonize sulfonamide activity, and you will have reduced activity of trimethoprim, or variation in the concentration of divalent ions like calcium and magnesium can affect the results of aminoglycosides, tetracycline, and also colistin with Pseudomonas aeruginosa, especially if you're using agar dilution method for colistin, that also can be affected. Now, how does this thickness and pH help? Suppose you have too shallow, then obviously the antibiotic will diffuse to a larger area, and it may give rise to a larger zone of inhibition. Depth which is more than 4 millimeter, that means if you have 5 mm plate or more, then it will result in a false resistance because it's a thick agar. pH which is less, then certain antibiotics like aminoglycosides, quinolones, and macrolides may lose their potency, and the other agents may appear to have excessive activity like tetracycline. And if the pH is more than 7.4, then the opposite of this might happen. If you use a heavy inoculum, then all the zone sites will be smaller. This you must have seen in your laboratory. If you don't match with the McFarland, either use a photometer or use these Vickram's card, they should be visible similarly with both the tubes that are there. Contamination is one big issue that we all have seen many times, and what happens here is that sometimes you can easily make out two zones, sometimes you can't make out these two zones, so it's best to repeat such a isolate. Then there may be a bad manipulation. What happens is that if you inoculate the plate with the help of flooding and not by swabbing, then this can happen and give rise to a large stent. Now, the drying of the agar plates, the surface should be dry, but it should not be too dry. You should not see cracks on the media or anything, because if there is a lot of moisture, there you'll have fuzzy zones. And if there is extremely dry, then what will happen is the antibiotic will not diffuse, because the antibiotic needs water in order to, become soluble and then travel through the media. So there should be no drops which are visible, but at the same time, there should be no cracks which are there on the media. So the storage of these plates, have to be done. Storage of these plates should be done at 4 to 8 degrees, and the drying, storage, and shelf life should be determined locally, whatever suits your this thing. Sometimes what happens is you have commercially available plates, so please store them as they are recommended by the manufacturer and use them within the labeled expiry date. Cartridges, antibiotic disc cartridges, store it at 8 degrees or frozen at minus 20 degrees. Take out only those which you want to require and follow a 15-15-15 rule. We'll come to the 15-15-15 rule in a short while. So these are the control strains. And remember, besides these 3 strains which I used, the E. coli 259, 22, Sood, and Staph, the other strains are required if you're, say, doing some research or your thesis where you require the 35218 or BAA 2814, or even for colistin or vancomycin production. The inoculum try to use the organism in a log phase of growth. That is why we say always use 4 to 6 hours, not beyond that, because then the expression of the genes will become different. Never use an undiluted overnight broth culture because it will not be standardized. Suspend it in a saline and make an organism if you think that the growth has gone beyond your requirement. And this is the methodology that we are all familiar with. 4 to 5 isolated colonies suspended in saline, adjust the McFarlane susceptibility and use it within 15 minutes of preparation. So 115 has already come here. See the Wickerham cards which is there. We've pasted one in our laboratory on the wall. Incubate them at 35 degrees. Never incubate plates in CO2 because there will be a decrease in the pH of the agar surface and it will result in the error due to the incorrect pH of the media. For staph against oxacillin and enterococcus against vancomycin, not 18 hours but 24 hours. And this is the biggest mistake because very often we put antibiotic sensitivity around 11 or 12 in the afternoon and report it the next day morning. So remember that it has to be read at 24 hours. While reading, do not use transmitted or magnifying glass. Never a magnifying glass. Measure it with the help of a vernier caliper or a scale. And never think that this is 20 millimeters. Oh, I see it every day. This looks like 16 millimeter. No, your eyes don't have a calculator. Try to use a vernier caliper or a scale. And once you get the hang of it, it makes your work much more easier. So very often you encounter these kind of things. So what you see here in the first one is basically there is no zone. If there is no zone, the C also has no zone. But here you see there is no antimicrobial effect because you don't even see the organisms. They're probably growing even beneath the disc. So probably the disc has not worked. Then in the second one, you see there are multiple colonies which are there. You see? So probably what has happened is that these colonies after 8, 16, 17 hours have started growing into this. And by the time you reported, you saw this. So it's either a potential resistance or a regrowth. You can't make it out. This could be a heteroresistance. This could be a regrowth. So just repeat. If you see this even on repeat, report it as a resistant this thing because there are too many colonies here. This is again an ambiguous outcome unless and until it is clearly demarcated zone like this. Do not report it as resistance. You see here what the problem is. They are growing here, and it's a very fuzzy, hazy zone. So other than the beta-lactam antibiotics, repeat it. Now, in case of D, you see a clear demarcated zone which is not disturbed by anything. This is what you should report as a true zone of inhibition. In addition to that, you will see that certain organisms with certain drugs will give you a different kind of picture. For example, certain enterobacterials with ampicillin or other beta-lactams will give you a fine growth after a clear demarcated zone that you can ignore. Similarly, E. coli and phosphomycin, if you use with G6PD, you will have certain isolated colonies within the inhibition zone that also you can ignore. Ignore swarming for proteus. Trimethoprim sulfamethoxazole with many organisms will give you a growth within the zone if the zone size can be seen, and even within when the zone size is substantial. For staph aureus penicillin, you will many times see heaped up zones. For cefoxitin, see that you don't see any colonies within the inhibition zone. For vancomycin also, look for any colonies within the zone. There might be a heteroresistance. So all these things you have to, pay real attention. This is about the fastidious organisms which are not much done. Do you think a bigger inhibition zone means that the organism is more susceptible or the antibiotic is more potent? Now, very often certain labs start reporting the zone sizes with their antibiotic report, and this is what the clinician infers from there. He feels that there is a bigger zone, so it is more susceptible. But you know as a microbiologist that a lighter bacteria, a lighter antibiotic will travel faster and will probably give rise to larger zones. Whereas the heavier antibiotics will have a slow level of diffusion. And as a result, the zone sizes may be smaller even for sensitive or resistant this thing. So never a zone size can be compared or MICs can be compared within drugs. Now, there are certain sources of error. This is what I was talking about, the 15-15-15 error. That means the suspension used within 15 minutes of making, discs applied within 15 minutes of lawn culture, and these plates are then incubated within 15 minutes. The plates, if they are not stored, their depth, the volume, the expiry date, the incubation conditions, incorrect inoculations can all give you wrong kind of readings, and the reading of the disc they usually remember. They know that this is CF is this and CFT is this, but maybe a new technician was there, or maybe they got distracted, and you will have an incorrect disc. And sometimes they put the disc the reverse, then also you feel that this is some other name which is written. So any incorrect storage, any labile agent, expiry agents which are not at room temperature, too many containers have been opened and they are putting it right from the container. Beta lactams, it's a huge problem. Very often I've seen laboratories, it happens in our lab also, that the imipenem, meropenem discs stop working because the discs have been left at room temperature. They are extremely sensitive to temperature, and their potency is incorrect. Too many discs if you apply, then you will not see clear zones. You will see what my guide used to call a chashma or a specs. Sorry, when one zone is interfering into the other zone, a 8-shaped structure. The control organisms again have to be correct. Now, I'm not going to talk about the dilution methods, just I'm going to mention that there are broth dilution, agar dilution, and then there are the e-test and the automated systems. Now, I'm going to talk about the CLSI. We all know how to read a CLSI document, don't we? As we think so. So, anything which talks about microbiology begins with M. Serial number of the document for disc diffusion is 02, whereas for MIC and dilution is 07. Remember that M100 only gives you tables for interpreting the results which are there as per the methodology which is mentioned in 02 and 07. But this is the standard that we most commonly use. It is A stands for approved, S stands for supplement, and the serial number after A gives you the number of addition. For example, 33 will give you 33. If it is an S, then it tells you that it is a supplement. 02 and 07 is revised every 3 years, whereas 100 is updated every year, and you always see something new. CLSI even organizes a webinar to update everybody as to what is new in CLSI, but it's a chargeable webinar. So when you're reporting these results, you will find that you've read about the breakpoints and you write susceptible, intermediate, and clinically resistant. And you should remember that these interpretive categories are actually based on microbiological characteristics, pharmacokinetic and pharmacodynamic parameters, and the clinical outcome data whenever it was available. That is why making an Indian guideline is such a difficult task, because then it will require that you not only use the microbiology characteristics from the lab, also correlate it with PKPD and also correlate with the outcome data if available. Only after all this does CLSI reach that particular level. So the MIC or the zone diameters which have been generated by this susceptibility testing are based on these established breakpoints, and we are all familiar with these breakpoints, that they are susceptible, dose dependent, intermediate, resistant, and non-susceptible. But always remember, when you're writing these, have you made your clinician understand as to what this is? Another thing is about ECOF. Very often you hear this terminology, particularly in conferences and from new PGs, that why don't we use UCAST? They are free to use, they are easily available, but majority of the laboratories still use CLSI. So the ECOFs, remember, are actually based on in vitro data. Lately, UCAST has started giving certain clinical breakpoints as well, but epidemiological cutoffs technically are based only on an in vitro data. They are not clinical breakpoints. They will only tell you what is the difference between a wild type population and a resistant population. A wild type population is a population of bacteria which has never experienced any resistance. It is the most naive kind of population, whereas the resistant population is something which has acquired a particular resistant gene or mechanism, like ma'am had elaborated a little while ago. So you can only label them as wild type and non-wild type. based on ECOF, do not report your sensitivity or resistant or anything. And we know this, that susceptible means that the isolates are inhibited by the achievable concentration. Resistant is that they are not achieved. The problem lies with intermediates. Intermediates is that the response rates may be lower, but you still want to use that agent in a situation where you know that it's a safer antibiotic and you can increase the dose. For example, from BD you can go to TDS, or from 100 mg in a day you can go up to 200 mg in a day. Or the agent may be efficacious if it gets concentrated in a particular site. For example, for UTI, you can use, even if you use an intermediate drug and it has got a renal excretion, it's likely to get concentrated in urine and achieve a high level which is above the MIC, and then it is going to kill that organism. So in these situations, you can use, and sometimes you want to provide a buffer zone, that prevents strains with borderline susceptibility from being incorrectly labeled as resistant. Now you have an organism which is resistant to everything, except one carbapenem to which it is intermediate. Now you would like to give this buffer zone to the clinician so as a colistin sparing agent, so maybe he can try it with that. So susceptibility, which is dose dependent, is actually as I would say, a step further than intermediate, where it is clearly defined that at what dose the susceptibility is there. Very often I'm asked this question, what is the difference between intermediate and SDD? SDD simply means that it has been defined in the document itself at what dose should you report at what sensitivity. So if your MIC is 2, then it is susceptible at a dose of 1 gram. But if your MIC is 4, then you can say that it's going to work if you give it 1 gram every 8 hourly or 2 gram every 2 hourly. So it becomes dose dependent. And very often these are now increasing. So very often you will find that they are being reported for more drug-bug combinations because they provide more clarity as compared to intermediate. So yes, they should replace intermediate if there is a higher frequency of resist dosing, which can achieve your therapeutic success. And it's better as an implementing tool for antimicrobial stewardship. Now, what is the difference between resistant and non-susceptible? Non-susceptible is when you do not have any resistant strain. Example is your Streptococcus pyogenes or group A, where you don't see any penicillin resistant in these strains. It's very rare. Then if you encounter one of these, you do not have any zone diameters for resistance in your laboratory which are there. In those cases, you report them as non-susceptible. You do not report them as resistant because resistance traits are not known. Now, when you use in the laboratory, you will find CLSI has got many tables. I still have about 10 minutes. So these tables are 1A, 1B, which I use for routine testing and reporting. 2A to 2L, where it gives you a criteria for interpretation, including the quality control. Then you have 3A to 3K, which give you a peculiar type of resistance. For example, colistin or ESBL. 1C to 2J are anaerobes, or one of those which are used a little. And an intermediate with an asterisk, inverted V in table 2, indicates the agents which have a potential to concentrate in the urine. So a lot of things to remember for you kids. Now, if you see your CLSI, you will find that there are routine tests, there are supplemental tests, there are screening tests, there are surrogate tests, and then there are equivalent agent tests. All these terminologies may confuse you, but they're actually very simple. Routine is routine, what you do routinely, perform the result, confirm the result, and report the drug. Routinely what you use. Say for staph, you have these 6 antibiotics which you use routinely. Supplemental are that you don't need an additional test, but they may be required sometimes and may be used as optional for reporting the clinical results. You may have a higher group of antibiotics may be kept in this where you want to report the supplemental results. So what are the various supplemental tests? For example, you want to do carba-NP and report how many of them are actually the carbapenem resistance is actually due to carbapenemases. Then you might want to do a colistin agar test for determining the colistin MIC. This actually should not be treated as a a supplemental test. It has now become a routine test with that kind of resistance that we have. And the oxacillin salt agar, because it detects this MEC also in addition to the cefoxitin, which is a surrogate marker. Then an inducible clindamycin resistance is something which we often use as a supplemental test and very, very commonly in the laboratories. So a screening agar test is something which is vancomycin screen agar or an high-level aminoglycoside resistance which we use. These are the screening agar, screening test, because here you are screening. So once you screen and you find that there is, yes, screen positive, then only you can report this, and you have to confirm it with MIC before you report this vancomycin. Now, please remember here, you look at this MIC of 6 micrograms per ml, which is there in vancomycin screen agar. So, ma'am was talking about visa. So, I want to miss a particular subset. Just think about it and put it in the chat box that if you're going to miss a particular subset, if you use vancomycin screen agar. High-level aminoglycoside resistance, technically, if the screen is inconclusive, only then you do an MIC. Otherwise, if it is not inconclusive, then you do it with Genta and Strepto both and report it as high-level aminoglycoside resistance. So this is what you should take. Now, what is a surrogate agent testing? Surrogate is that you don't test the actual one, but you test it with another drug. Most common example which is used here is cefoxitin, which we use for MRSA, because we know that cefoxitin, the surrogate, performs better than the agent of interest. For example, if I were to use methicillin or oxacillin, I will have to make a media which has high salt. I will have to set my incubator at 30 degrees and will have to measure it for 18 to 24 hours, not 16 to 18 hours. So instead of that, cefoxitin can be put. Now, if you have to make a media, put in another incubator, that means you need one plate for staph for methicillin resistance only. So that is why the surrogate cefoxitin performs so much better for all. But remember that it predicts resistance to MEC-A-mediated methicillin resistance only, not for MEC-C. If you were looking for any other mechanism other than MEC-A, you might require to do methicillin or oxacillin resistance. Cefazolin, it predicts for all uncomplicated UTI, that means no upper UTI, only the lower uncomplicated UTIs. For all the oral cephalosporins, it is tested as a surrogate marker. It's very commonly followed in the West. In India, we do not follow it much. Similarly, pfloxacin for ciprofloxacin. In India, we often use ciprofloxacin itself. We don't use pfloxacin. So we don't use this as a surrogate marker. But the West uses it. Then the equivalent agent testing. Can you think of any drug which is an equivalent agent? That means that it will predict the sensitivity to the other drug. These are mentioned with an or. For example, cefotaxime or ceftriaxone, colistin or polymyxin. Most interesting is macrolides, azithromycin or clarithromycin or erythromycin. So if you do any one, it predicts sensitivity to all these. Penicillin susceptible staph are susceptible to other beta-lactams with established efficacy for staph infections. Then resistant ones are resistant to all penicillinase labile penicillins. The results of ampicillin susceptibility can be used for amoxicillin for Haemophilus, and the ampicillin can be used to predict amoxicillin for anaerobe cyst. So these are the equivalent agents that we know of. So for staph, you see azithro, clarithro, erythro, which tells you that it is yes. Now 1A, as I said, is for the primary test report, which is used. Now group B mentions that it is optional or primary. Now there are certain warnings which are there in CLSI. For example, there is a warning that following combinations should not be checked. Now this is a classic example of in vitro to in vivo. For example, Salmonella Shigella may appear very effective in vitro, but do not work for in vivo. First and second generation cephalosporin, cefamycin, and aminoglycosides. Similarly, for enterococcus, aminoglycosides, except for high-level resistant testing, cephalosporins, clindamycin, and Septron or trimethylsulfamethoxazole is not going to work. And for any bacteria which is isolated from CSF, Any of the oral agents, clindamycin, tetracycline, macrolide, cephalosporin, cefamycin, carbapenem, and fluoroquinolone are not going to work. Sometimes there is a confusion in the antibiotic lab. They don't know from where this organism is coming from. And they write this, but remember while reporting, write a note there that these are not going to work in meningitis. Fecal salmonella and shigella, ampicillin, cotrimoxazole, and fluoroquinolone. For extra intestinal salmonella, add a third generation cephalosporin to the above. Chloramphenicol and azithromycin upon request, or if your center uses these drugs to treat, because what happens is this happens very commonly in typhoidal salmonella. Azithromycin is not a killer, it's a bacteriostatic organism, and the therapy again so you might again have a discordant between vivo and vitro. Then if you have an intestinal source, non-typhoidal salmonella, DST is not recommended. And again, if you have an extra intestinal or intestinal, then AST is recommended for all Shigella and typhoidal salmonella. So this I've already covered. Don't report UTI again for macrolides, clindamycin, minocycline, and chloramphenicol. Any drug which is not excreted through urine or kidney should not be reported for UTI. CSF I've already covered. So always remember that the organism which is susceptible to tetracycline is also considered susceptible to doxy and mino. However, you may have certain strains of tetracycline which may be susceptible to doxy or both. Remember the intrinsic resistant, I have not covered because ma'am had already covered intrinsic resistance, but always remember you cannot report Pseudomonas to ampicillin or trimethoprim or sulfamethoxazole because it's not going to work at all. Daptomycin is not recorded for respiratory isolates because it gets inhibited by surfactants. Phosphomycin always needs glucose 6-phosphate. So remember that the disc has to have that amount of chemical. So thank you so much for joining. And if you have a question, please put it in the chat box. As far as I can see, there is just one question. What is cation adjusted Muller-Hinton agar? And you want to see the slide again. Actually, see, cation adjusted Muller-Hinton agar is in which calcium and magnesium concentration is adjusted to the best. It's lowest possible because they are going to interfere with your sensitivity testing. You can use any other broth instead of saline. If you are using making a suspension, then only saline is recommended because these are the standardized methods. We don't deviate from them. And the SOPs are based on those standardized methods. So there are no more questions, I think. So I will now hand over to Dr. Pallab Ray, who needs no introduction. He's from PGI Chandigarh. He was ex-HOD there. And whatever you heard from me, I think I've learned a lot from him and from my guide, Dr. Krishna Prakash, on antibiotics. So over to you, sir, now for the rest of the automation.
Thank you, Dr. Sonal. I thank Dr. Anuj for being here with us. And thank both the presenters for two excellent presentations. Can you see my screen and hear me?
Yes, sir, we can.
Okay, fine. So then let me start. I am supposed to talk about emerging tech. I am supposed to talk about automation in AST. But I have titled it as Emerging Technologies and Automation in Antibiotic Susceptibility Testing. Now, let me first start with a few comments which have already been made by the previous speakers as well as Dr. Anuj Sharma. Now, antimicrobial resistance is one of the largest global health threats in the 21st century. And it demands urgent measures because the emergence of antimicrobial resistance is converting common infections into untreatable conditions. And we have already heard that it's projected that by 2050, there will be 10 million deaths in 1 year due to drug-resistant infections. Now, the main drivers of antimicrobial resistance is improper use, overuse, underuse, or abuse. So, to minimize the improper use of antibiotics and spread of AMR, it's important to confirm the infectious pathology. We have to confirm that this pathology is due to an infection and not due to inflammation due to non-infectious etiologies. We have to differentiate non-bacterial versus the bacterial infection. And we have to shift very fast from empiric to definitive therapy, antibiotic therapy. And for shifting from empiric to definitive therapy, we need identity of the etiological pathogen and to detect antimicrobial sensitivity or resistance in microbes. And finally, to find antimicrobial agent best for cure. So my presentation will concentrate on detection of antimicrobial sensitivity or resistance in microbes. Now, since this particular topic or antimicrobial resistance and sensitivity detection is closely related to identification of the etiological pathogen. So you will see that many of the systems which use rapid or automated detection of antimicrobial resistance, they are also coupled with identification of the etiological pathogen. Truly speaking, identification of the etiological pathogen is one of the essential prerequisites for detection of antimicrobial susceptibility or resistance in microbes. There is an urgent need to bring diagnostics closer to practitioners as well as the patient, and this can lead to a paradigm shift from empirical to evidence-based treatment of infectious diseases. Now, you know that requires automated and rapid diagnostics for both pathogen identification and antibiotic susceptibility testing. Currently, the antibiotic susceptibility testing that we carry out, it requires pure culture isolates, and we try to see the effects of drug on growth of these pure cultures. Now, this is because the different types of samples with its inhibitory effects and other components, the number and the load of different microbial species, they vary in polymicrobial samples, particularly the samples which come from the respiratory and the urinary tract, and those two conditions probably constitute the maximum number of patients which attend the outpatient clinics. Now, the typical growth-based antibiotic susceptibility testing, it requires several cultivation rounds. The enrichment cultivation, which we carry out in blood culture bottles to increase the number of bacteria, then plate cultivations for pure cultures, then antibiotic susceptibility testing for liquid or plate cultures by broth microdilution, disc diffusion, gradient tests, agar dilution, breakpoint tests, and which are actually based on continuous exposure of the isolate to antimicrobials, leading to visual detection of growth. Actually, let me tell you one very important thing to all the students. You know, it's a battle between the bug and the drug. And the results of the bug and the drug, they are decided within 2, 3, or 4 generation times of the organism when both of them, they are exposed to each other. It's only our failure to detect which organisms are alive and which organisms are dead, because we have been using the same technique which Robert Koch showed us 140 years back, that when an organism is inoculated on a solid media, it produces a colony after, say, 18 hours. So that's why we take 18 hours to know which organisms are alive and which organisms are unable to grow to a colony. Now, if we have methods which can tell us which organisms are alive and which organisms are growing, so if we can differentiate between the two, then probably we can report it much faster. So this whole procedure, it requires several days' time. So this particular diagram shows the steps. We have sampling, then microscopy, identification, which can be a quick identification by MALDI-TOF or molecular methods like FISH immunodiagnostics, nucleic acid amplification technology, or identification by the conventional methods, and then growth-based AST, which gives us result after 36 to 72 hours. Now, if we can avoid that rapid ID or AST from the pure culture level, and after that, if we can avoid the growth-based antibiotic susceptibility testing, that we can get the results within 30 to 40 hours. And then if we have rapid antibiotic susceptibility testing from the clinical specimen itself, then we can diminish it to 0.5 to 8 hours. That's actually why we require modern tools for rapid and automated methods of antibiotic susceptibility testing. So let us go into what are the innovations and the techniques that have made these automated systems, rapid systems possible. So let me first start with certain limitations of my presentations, that I have limited my presentation mainly to bacterial antibiotic susceptibility testing. Secondly, I want to admit that in the last 3 decades, there has been huge technological advancements, and there is a huge amount of work going on newer methods of antibiotic susceptibility testing. Hundreds of groups of scientists are working on it worldwide. So it's not possible to talk about all the technologies in half an hour. So I can only give you a snapshot of trends and technologies which are actually going on in this particular field. So there has been lots of innovations and new approaches in electronics, biosensor techniques, optics, microfluidics, hybridization technologies, DNA amplification technologies. There has been newer techniques which exploit progress in nucleic acid amplification, in electrochemical methods, microarrays, micro and nanotechnologies, and the mass spectrometry applications. But let me admit that very few of the newer molecular methods, they have got FDA approval. And scientific papers on these technologies do not sufficiently relate to the practical needs of a point of care test right now. This is a chart which I have made myself to explain how the innovations and techniques work. Let me start with the clinical bacterial isolate. So we have already spent time on clinical bacterial isolate. So we carry out identification and antibiotic susceptibility testing. How do we carry out? By in vitro growth-dependent tests, by mixing up bacteria with antibiotic and then growing them. So the growth may be a conventional growth that we carry out in case of disc diffusion and other tests, which can be an accelerated growth, which happens in case of the currently available semi-automated systems. And the antibiotic to which the bacteria are exposed, the antibiotics may be a continuous gradient, like in disc diffusion test, in the e-test. It can be a discontinuous twofold levels of antibiotic concentrations, as we carry out in agar or broth dilution, or it can be a few breakpoint concentrations, that is what we carry out in case of agar and broth dilution. And how do you read the results? If we read the result by visible growth, a colony on agar, it takes 18 to 24 hours. If we look at turbidity in broth, it can take 4 to 24 hours. If we can read the result with the help of a microscope, then the colony on agar can be seen even within, say, 4 to 6 hours. if we can detect metabolites produced by the growing organisms like proteins, enzymes, using MALDI-TOF mass spectrometry or using immunodetection, it can be even more rapid. And then we have a plethora of growth-independent technologies where the bacteria, with or without antibiotic, is subjected to different technologies like nucleic acid amplification, PCR, various types of PCR, RT-PCR, cDNA RT-PCR, hybridization, microarray, microfluidics, photon excitation fluoroscopy, Raman spectroscopy, a ligase chain reaction, strand displacement, NASPA, LAMP. So if you look at it right now, we are following this particular method and reading the result by this particular method. And therefore, it takes hours, even days for getting the results. So the newer methods, the automated, newer innovative techniques, they exploit these techniques rather than the old-fashioned growth-dependent techniques. These techniques are growth-dependent, but detect them much faster than a visual appreciation of colony on agar or turbidity in broth. So we already have lots of semi-automated commercial systems. We have the Vitek, the microscan systems, which are dependent on automated turbidity measurement for multi-well liquid cultures. We have Phoenix system, which exploits redox indicator to enhance detection of growth. We have an Alfed 60 AST system, which exploits laser light scattering to detect growth in liquid culture. And if you look at it, these methods, the turnaround time for identification is 4 hours. For antibiotic susceptibility testing is anywhere from 4 to 6 hours and more. And in practice, we have already seen, because many of us, we are using these systems. In practicality, it takes somewhere around 12 to 18 hours. The Alfed 60 AST system, the turnaround time is 4 to 6 hours because it uses a better, more recent technology of laser light scattering to detect growth in liquid culture. All these systems, they are broth dilution-based, semi-automated, accelerated growth systems. They use proprietary ready-made antibiotic susceptibility test cassettes or cards like this. And the cards, they contain positive controls. They contain whales with increasing concentrations of antibiotics around the breakpoint. And they provide continuous growth monitoring. And they can analyze the MIC patterns for a large group of organisms against their extensive databases. Now coming to that, the pathogen identification is one of the most essential preliminary step of antibiotic susceptibility testing. Now, if we can have a quick identification, then we can customize the search palette for the antibiotics. Now, mass spectrometry MALDI-TOF is a versatile workhorse routinely applied for bacterial identification nowadays in many of the laboratories. The MALDI-TOF semi-quantitative growth rate data by Bruker, the BT star Carba assay can even give us antibiotic susceptibility test based on antibiotic degradation monitoring using mass spectrometry, and we can have very rapid results of Carba assay, and thereby we can interpret how the antibiotic will work on that particular isolate. There are antibiotic susceptibility tests for blood cultures after short-term cultivation on agar plates, and then followed by antibiotic susceptibility testing using Vitek AST cards selected by MALDI-TOF analysis. There are limited direct antibiotic susceptibility tests recommended from positive blood culture bottles by both CLSI and UCAST. You can get them in the CLSI M100 and the UCAST documents. Now let me come to from the semi-automated growth-based approaches to some of the novel approaches. The first novel approach is a microscopy. You know that to detect growth, microscopy can detect growth long before they produce visible colonies. E. coli colonies visible by eye need 5 million bacteria, whereas microcolonies of only 120 cells can be detected by microscopy. And therefore, we have microscopic observation drug susceptibility MODS for Mycobacterium tuberculosis, which makes the process much more rapid. We have growth direct system by rapid microbiosystems, which detects microcolonies with digital imaging with blue light cellular autofluorescence directly onto a CCD chip in 3.1 hours time. And clinical studies of efficacy of this particular system is going on. There are automated microscopies methods which provide quantitative bacterial counts and real-time growth curves. And we have certain systems available on that technology also. Multiplex automated digital microscopy by MADM from Accelerated Diagnostics, which employs fluorescent in situ hybridization for rapid online antibiotic susceptibility testing. And we have this particular system, Accelerate Pheno system. This is a very important system because it first separates in an automated fashion, it separates impurities from samples by electrophoresis into a gel, reverses polarity to repel the microbes back to the liquid, and then there is a fluorescence signal detected every 10 minutes from bacterial culture in Muller-Hinton broth. This is the only FDA-approved growth-based rapid AST system, microscopy-based, with many clinical studies which have shown its efficacy. Turnaround time for identification is 1.5 hours. For antibiotic susceptibility test is 7 hours. Now, let me come to nucleic acid amplification technology, which is exploited by many of the systems which are already available in the market. Remember that the first generation molecular tests like RFLP, PFG, multilocus tandem repeat analysis, MLST, virulence genotyping, they require large amount of DNA and purified DNA. They're suitable for typing outbreak investigations, but not antibiotic susceptibility. They don't allow rapid diagnostics. Therefore, people use hybridization-based approaches and molecular beacon systems with nucleic acid amplification tests. There are many diagnostic panels which detect specific syndrome-based limited antibiotic resistance genes. And we have bioMérieux, Elitech, Bosch, Iplex, QIAGEN, BD. They have their own systems which are based on this particular technology. Remember that detection of antibiotic resistance genes is not undisputed proof of antimicrobial resistance, because AR genes are not necessarily, they don't necessarily relate to pathogen causing disease in a multi-organism unsterile specimen. The resistant gene may not be necessarily expressed, and NAT neither defines MICs nor indicates which antibiotics should be used. Now, we come to further modifications of NAT. The qPCR allows rough quantification of microbes, and qRT-PCR also assess expression level of resistance genes exposed to different antibiotic loads, and therefore give rough MIC values and tell us about also expression of the gene. But the problem is the cost of qRT-PCR is currently far beyond acceptable for routine AST. A few words generally about NAT is it's a powerful tool for identification of bacterial viral pathogens, allows use of patient samples without culture. Several target genes can be tested in the same sample using different fluorescent levels. The risk of losing but the problem is risk of losing template during nucleic acid extraction, it diminishes sensitivity, and sensitivity of DNA polymerases to impurities also gives us false negative results, and some of them require separate kits for DNA extraction and separate kit for PCR. Coming to other novel approaches, we have NAT, nucleic acid hybridization, immunodiagnostics, which allow us use non-purified polymicrobial clinical samples directly without culture. Now, short cultivation with predetermined antibiotic load and followed by NAT isothermal amplification can reveal antibiotic resistance and also give us rough MIC. But the problem is many novel methods use pure isolates. They claim antibiotic susceptibility testing in minutes to hours by ignoring time for enrichment culture, isolation of pure cultures. They will tell you our system can give you results within say 4 hours, but they ignore the time to grow the organism, purify the organism. That itself takes 1 to 2 days. Most of the rapid growth-based AST methods, they perform endpoint analysis only and not continuous monitoring. The fast, reliable, easy, inexpensive systems applicable to outpatients, it is actually still elusive. Coming to systems which can reach further sensitivity and specificity by applying hybridization to DNA microarrays. There are many FDA-approved multiplex diagnostic panels. They're already available. We have the ExpertR, Univero, BDMax, SafetyFast, MagicPlex, ePlex, Novodiag, Genome Era, and some of them, the first few, they are available as cartridge-based nucleic acid amplification tests also. There is a very promising system from T2 Biosystems where a test panel detects 13 resistance genes from gram-positive and negative pathogens directly from blood by magnetic resonance after hybridization with DNA probes conjugated with super paramagnetic particles. And then there are a couple of other systems which are right now applicable to detecting the organisms, but they are now coming up with antibiotic susceptibility testing panels. This particular one detects more than 750 different bacterial species in a single test. And this is by Thermo Fisher, the high-resolution melting system. It identifies variation in nucleic acid sequence through very small differences in PCR melting curves. Some of the other new technologies, there are new enzymes and technologies, the ligase chain reaction, NASBA, strand displacement amplification, LAMP, they are coming up in antibiotic susceptibility testing. They have simplified nucleic acid amplification. They are more robust, often allowing use of samples without even nucleic acid extraction. They have enabled miniaturization. They cut down the costs of instrumentation by allowing isothermal nucleic acid amplification. LCR can also be easily integrated into other detection systems. There are so many other detection systems to which it can be integrated. There is, by bioMérieux, a platform called NucliSensor EasyQR. This is the first automated system which combines NASBA and real-time detection using molecular beacon probes, enabling first detection of Klebsiella carbapenemase genes. Similarly, there are other robust LAMP-based systems available. Coming to immunodetection, I have a couple of slides on immunodetection because even this system is coming up from different scientist groups. The importance is that immunodetection leads to specific and sensitive methods for identity of bacteria and viruses, and the immunological binding does not disrupt the target microbes. Therefore, they provide pathogen identification and growth kinetics in a single step. They can be adapted to simple lateral flow tests. Therefore, they're good for but the problem is they're good for purified clinical isolates, not specimens directly. They can be integrated to biosensor technology, microfluidics, or DNA RNA-based analysis. there are already a few of the platforms easy to use stick tests for clinical diagnosis of influenza viruses and bacteria causing STDs by immunodiagnostics, but there are only few products available for direct detection of antimicrobial resistance proteins, and they are limited to maybe single antibiotic resistance by a single species of organism, like chloramphenicol resistance in Pseudomonas or methicillin resistance in Staph aureus, or carbapenemases, limited number of carbapenemases. There is one Mary-POCR system by ArcDia Limited, which exploits 2-photon excitation fluoroscopy technology. And this is already in diagnostic use for immunogenic detection of pathogens, but not right now adapted to antibiotic susceptibility testing. A few of the future technologies: mass spectrometry is likely to become tightly integrated into other AST technologies, especially in the diagnosis of septicemia. We already have MALDI-TOF direct on-target microdroplet growth assay, .MGA sample. It uses sample droplets culture plus antibiotics in different concentrations in 6 microliter volumes, spotted directly onto disposable target plates of mass spectrometry, incubated for 3 to 4 hours, analyzed with mass spectrometry, and giving the growth kinetics and interpreted as drug susceptibility or resistance. There are screening panels for ESBL and AMC beta-lactamases, and kits are available for enterobacterials already with the help of mass spectrometry. There are a few groups who are working on time-lapse microscopy, and they have come up with certain kits like Quick MIC, Q-Linea Astra R, Oscilloscope TM. So these are digital time-lapse angled field microscopy. The time to get a result from positive blood culture bottles is 1 to 4.2 hours, but they are the clinical efficacy is right now going on, and we are waiting for the results. Even people are working on growth-independent changes in individual cell morphology on exposure to antibiotics, because individual cell morphology changes or size indicate growth long before bacteria have multiplied. So there are systems of using single cell morphological analysis using bright field microscopy to determine antibiotic-induced changes in cells immobilized on an agarose channel chip. So there is a particular platform called Multipath TM, which exploits this particular system. I must here mention about the GoFast or nanostring technology, because it combines genotypic and phenotypic AST through RNA detection. It detects messenger RNA expression signatures after antibiotic exposure, can be used directly for positive blood culture bottles, and couples machine learning analysis of transcriptional changes with detection of resistance genes. So we already know that whole genome sequencing is a feasible system for pathogen identification and antibiotic susceptibility testing. We have many third-generation systems, the Illumina Minisec, PacBio Sequel, Oxford Nanopore Minion, and Promethean. Whole genome sequencing can simultaneously provide pathogen ID, epidemiological typing, as well as drug susceptibility genes. But the problem is that right now, in 2017, UCAST concluded that for most bacteria, the available evidence for whole genome sequencing as a routine AST tool is still emerging and thus inadequate for clinical decision making. And the situation has not changed much even after 5 years. But with cheaper and cheaper whole genome sequencing and faster whole genome sequencing platforms coming up, it may show promise in near future. To conclude, the standard growth-based technologies based on disk diffusion and broth dilution still dominate in AST. They are slow, They require pure cultures, but they serve the purpose pretty well with extensive experience and correlation studies carried on over the last 5 decades. Only few rapid growth-based AST methods work directly with polymicrobial clinical samples, which is required in point-of-care tests. The sensitive growth monitoring can be achieved either by frequent sampling or by online immunodiagnostic methods. Digital antibiotic susceptibility testing plus chip-based microfluidics and isothermal amplification can revolutionize phenotypic AST in near future. Fish-based Accelerate Pheno system already has reached FDA approval. And I end with 2 comments. However, the new emerging technologies, they struggle to meet all criteria that Professor Kalmeter set for AST technologies. Are they generally applicable or restricted to certain infections? What is their capacity? How many organisms or agents per hour can be processed? Has the technology been validated against reference methods? Are there any reference installations? Is scientific literature available? When it will be available on market? No technology available right now is optimal in all aspects. Many will reach a large customer base. Consensus statement of the PIAMR AMR RDT working group on antimicrobial resistance and rapid diagnostic testing made in 2019 is still valid. There is no single major or broadly accepted technological breakthrough that leads the field of rapid AST platform development right now. Thank you very much for your kind attention.
Thank you very much, sir. There are a few unrelated queries in the chat box. Talking about what we are going to do. Can we have a uniform medical code or drugs in order? I don't think this is the basics of this forum or it deals with it. But if you have any technological issue, please, or if you found any particular topic which was not required by you or which you need more elaboration, please let us know in your chat box. The only way, but we have a full house, almost a full house.
Yes.
And I thank Dr. Rajni and Dr. Pallab Reza for this extremely informative and knowledgeable session. And Dr. Anuj had to leave for another meeting, but as you all can see in the chat box, 24th of November is the Go Blue Day. And I think all of us should be in our Go Blue uniforms of antimicrobial resistance fighting. So remember that and post it on your social media with hashtag AMR. If any of you were late in joining or missed anything, you can see the same recording on our YouTube live. We are currently also live on YouTube channel of IAMM PG Masterclass. So thank you very much, sir, and Dr. Rajni once again.
Thank you. Thank you, Dr. Sonal.
Thank you, Dr. Sonal. Thank you, sir, for very informative lecture.
And very interesting.
Yeah, very interesting, of course. And even yours one was very interesting, Dr. Sonal. Very informative for PGs and for everyone.
Somebody is saying that they got to know about this very late. I've been sharing it for past 2 weeks, but now go on YouTube and watch it. On YouTube, if you Google IAMM PG Masterclass, there is only one hit there with that name. So thank you so much once again for joining.
Thank you. Thank you so much. Good night.